Hello everyone, this is Dr. Young, and in this video we're going to talk about the E2 reactions. And again, I'm going to apologize from the very beginning because this is going to be a long video. There's a lot to think about when it comes to E2. It's probably one of the more complicated ones just in terms of things you need to worry about. So I apologize. I thought about breaking it into two videos, but that would just, I just like the idea of everything being in one video so you can find it more easily. So by all means, stop halfway through, digest, take a break, practice something, look at your notes, and then finish the rest of the video if you have to. But it's gonna be a long one. So E2, the E stands for elimination, right? So I have an example down here, and if you take a look at the molecule over here on the left, this sucker, the idea is if I take the formula, it looks like I've got 1, 2, 3, 4 carbons, I've got 9 hydrogens, and I've got a bromine. And if I look over to the right-hand side, I still have 4 carbons. Now I have 8 hydrogens and no bromine. So what I did was, as I went from left to right here, I lost things, right? I lost the bromine, and I lost a hydrogen. All right, if you look at those formulas, I have 1 fewer hydrogen, and now I don't have a bromine. And so when we're looking at these eliminations, what you're always going to see is that you eliminate 2 things. Eliminate 2 things. One is going to be the leaving group, which is perhaps not a surprise. They're called leaving groups. They're going to leave, right? So anything that's going to come off and be really stable, so really weak bases, things like that. And the other thing that you're going to lose is a hydrogen. But what we're going to see is that it's not just any hydrogen. It has to be one away from the leaving group. It has to be on the adjacent carbon. Or another way to say that is that it has to be beta to the hydrogen. So the other thing you're going to remove is a hydrogen on the beta carbon. All right, so your Greek lowercase beta. And so what is beta? What are we talking about here? You may have already learned the alpha, beta, gamma, delta system. It's just a way, it's not really IUPAC. You wouldn't say like I've got beta, bromo, propane or something like that. It's just a way to talk about how many carbons away from a certain functional group are you. So for us, we have an alkyl halide, so the functional group piece is really the halogen, the leaving group. So if I look at the first carbon that it's attached to right here, this bromine, that would be the alpha carbon. That's the first carbon, right? The first letter of the Greek alphabet corresponds to the first carbon. And then anything that's 2 away would be the beta. 3 away would be gamma. 4 away would be delta. And you just keep on going down the Greek alphabet. You're really not going to see too much further past beta. Maybe you might see gamma one day, but alpha and beta are used all the time in OChem. So that would be an alpha carbon. And then this would be a beta carbon because it's 2 away from the bromine. But this is also 2 away from the bromine. And this is also 2 away from the bromine. So I actually have 3 beta carbons with 3 sets of hydrogens that I could eliminate. And if you notice, it looks like this was the one, this hydrogen here was the one that was eliminated on that beta carbon because I don't see it over here, right? Now this is a CH2. It was a CH3 to begin with. So I did lose that hydrogen. When we look at our E2 kinetics, it is all the 2 again, just like SN2 stands for second order and that it's bimolecular. So if I take a look at its rate law, it's going to be the same sort of thing as SN2's, right, where my rate equals some rate constant that's determined experimentally times the concentration of 2 different things. And much like SN2's, it's going to be the substrate, right? How much substrate do you have? That's going to determine how quick it is. But the other thing is, before we put nucleophile for the SN2s, because we use nucleophiles to substitute things out. But in this case, if I need to remove a hydrogen, right? The molecules that we use to pick up hydrogens are bases. So we need a strong base. So for these eliminations, you need a strong base. And by strong base, I mean anything stronger than hydroxide or stronger, those nice strong bases. So the other thing in the square brackets is how much base do you have? The more base you have, the faster it goes. The more substrate you have, the faster it goes. So it's bimolecular. Now let's look a little bit at this mechanism. Like the SN2, this is also a one-step mechanism. It's also going to be one step, or in other words, concerted. which is why it's bimolecular. It's one step, so both of the reagents matter. They're both involved in the only step that there is. Now, one other thing that we need to kind of take into consideration here, I also said that, I need to know what's going on with the base type. If I'm looking at the base type here, I'll do this in green. If I'm looking at the base type, what I mean is not strong or weak, because all of these bases have to be strong. What I mean is your base unhindered or hindered? Unhindered or hindered? And so, or in other words, is it small or is it bulky? Right? How much branching is there on your base? Is it small or is it bulky? How big is it? Let me write that a little bit cleaner. And so let's take a look at this. Let's say I'm going to go in one direction. I'm going to use a base like this. So I'll use Na plus and O CH3, CH3, CH3. So this would be sodium T-butoxide. Tertiary butoxide, right? Because that carbon attached to the O is a tertiary carbon. Or let's say instead I'm going to use a different base. Let's say I use, in this case, sodium methoxide. Right, meth oxide, because there's just a methyl group on the oxygen, so meth oxide. Now, if you look at the two of these, right, hopefully you can see these, and one of them is definitely bulkier than the other one. One's a small base, one's a large base. One's an unhindered base, one's a hindered base. And you're just looking for branching. So this T-butoxide one, right, the one on the left, the one in blue, is definitely considered a bulky hindered base. Definitely bulky, definitely large. Sodium methoxide, all it's got is one methyl group on there. That's tiny. That's not a big deal, right? So that would be a small unhindered base. And what we're going to see is that they're going to kind of react differently. You're going to get different major products. Now, I'll start with my T-butoxide. We'll do that one first. But I want to point out here, right, we said we're going to remove two things. We said that we were going to remove the leaving group. Check, here's my leaving group. I've got the chlorine on there, right? That's the thing that's going to be the most stable when it comes off. A Cl- is nice and stable, real weak base. And then if I take a look at my molecule, I also need to find the beta hydrogen that I'm going to take off. So if I look here, here's my alpha carbon, the one directly attached to the chlorine, and it looks like in this case I have two beta carbons, one to the left and one to the right, which means I can either take off any of these hydrogens on that beta carbon, those are all beta hydrogens, or on the right-hand side, I can take off just one, right? The right-hand carbon, the right-hand beta carbon only has one hydrogen on it. The other two things attached are methyl groups. So really there's four hydrogens that are options that I could take off to do this elimination, and I'll show you the mechanism in a second. But what I need to consider here is that I've got this big old base, right, my T-butoxide, the stuff in blue, and I have options, right? I can either have my base go and attack this primary carbon over here, this beta carbon on the left, or the carbon on the right is a tertiary carbon. And so you want to be thinking about sterics. What kind of steric interaction is there? Is it going to be easier for my big bulky base to go get the hydrogen in the tertiary spot with all the groups? Or is it going to be easier for my big bulky base to go to the primary spot where there's less stuff in the way, where there's less steric interactions or fewer steric interactions? And if we think about this, right, it's just that the big bulky bases are going to be able to get to the less substituted place easier. It's just going to be a lower activation energy, fewer steric interactions. And so what you're going to see is that your big bulky bases tend to go for the hydrogens on the less substituted carbon. Right? Your big bulky bases remove hydrogens from the less substituted carbon. And let me write that actually. Well, let me finish the mechanism. So your base is going to go get an H, like all bases do, all of the time, right? So it's going to go pluck out that hydrogen, but those two electrons can't make a new bond with the hydrogen, and then hydrogen has two bonds. Those electrons from the CH bond need to break. And what happens is they break and they fall down between the alpha and the beta carbon so that you get the double bond from your elimination, right? So if you looked at that previous slide, we made an alkene, we have a double bond. But same thing, that alpha carbon can't have 5 bonds, and so it has to kick something out. What does it kick out? The leaving group, right? The leaving group is going to leave, so that's going to get kicked out. So all of this happens in one step, all at once. These 3 arrows, boom, 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 all of the electrons move through those orbitals, and that reaction occurs right there. And so what you're going to get here, if I draw out the product, is we should end up with something that looks like this. La-di-da. Or if you wanted to do a line bond drawing, you could have drawn this, right, where your original product was this. And I'm drawing out the Lewis structures just so you can see all the hydrogens so we can talk about them. But line bond drawing, same thing, works fine. And this would be your major product if you used a big bulky base, right? So this would be your major product. Now, what we're going to see, I'm just going to let the cat out of the bag now. What we're going to see is that if I use a small base, so this stuff in purple, the sodium methoxide, what I'm going to get is going to be a different alkene as my major product. What I'm going to get is that we remove the other set of hydrogens instead. To get this product. What we're going to have is that the purple methoxide here, because it's small, the small one actually is going to give you more product where it takes off the other beta hydrogen. Again, these electrons drop down. Again, the electrons kick up so that the chlorine can leave. Again, all concerted. It's the same mechanism, just in a different spot, to give us a different major product. Right? So now this is the major product for a small base. So you should be asking yourself, well, why? Why does it switch? Why is it going to be different? And the difference is, and you may have already learned this when you talk about alkenes, but if you haven't, you want to remember that the more substituted alkene is more stable. So if you have a tri-substituted alkene, that's more stable than a mono-substituted alkene. A tetra-substituted alkene is going to be the most stable. So if I look at this, right, so this major product, this is the major product because it's the most stable alkene. And I identify it as being most stable because it's the most substituted. It's the most substituted alkene. Because if you look at this alkene, what we have coming off the alkene is we have 1, 2, 3 groups coming off of it. So it's tri-substituted. It's a tri-substitute alkene because it has 3 carbon groups coming off. You don't count all the carbons, like if it's a long chain of like 10, you don't count all 10 carbons in that decyl group. You're just saying of the 4 things that could come off of the alkene, how many of those 4 are carbon-based groups? How many of them are alkyl groups? So tri-substituted. Now if I look over at the other alkene, right, this one is less stable. I'll even put that. It is less stable. And that's because if you look at this alkene, all of the groups that are on it only has 1 carbon group coming off, right? The other 3 things coming off that alkene are just hydrogens. So this would only be a mono-substituted alkene. It's only a mono-substituted, right? It only has 1 alkyl group, 1 carbon group coming off of it, as opposed to 3 like the other one. And again, we're talking about the things coming off of the carbons in the alkene. These different products have names. One is Zaitsev, one is Hofmann. If you're going with a big bulky base, you're going to be forming what's called the Hofmann product. This is often called the Hofmann product. The less stable, the less substituted alkene is the Hofmann product. If you're looking at you use a small base and your alkene predominantly forms the more stable product, that's called the Zaitsev product. The Zaitsev product. Zaitsev, just as a side note, I think this is how our book spells it. Different books spell it different ways. We're We're not really great at spelling these Russian names super well. So if you see like an S instead of a Z for Zaitsev or an F instead of a V for Zaitsev, it is the same person. They're talking about the same thing. So Zaitsev product is the more stable alkene. The Hofmann product is the less stable alkene. And this is just based on, did you pick a big bulky base or did you pick a small unhindered base, right? An unhindered base gives you Zaitsev, a hindered base gives you Hofmann as your major product. So let's look at these energy diagrams real quick. I think we did establish, right, hopefully that, so here's my starting material, I'll draw this, boom. And I think we just established here that the more substituted alkene is the more stable one. So I'm going to draw that as lower energy, right? So we've got the lower energy, more stable alkene, slightly lower. And if we do this, right, if I talk about the fact that I'm going to use an unhindered base here, so I think I had methoxide, right, in that previous slide. If I have the methoxide attack the less substituted one, that is going to give me, that's going to get me here to this less substituted alkene. If I have it attack the more substituted one, then I'm going to get to the more stable alkene. So I'm simply going to have a lower energy, or lower activation energy, E sub A, or you could say delta G double dagger, to give us the most stable product, right? Here's our more stable product. So you tend to get primarily that more substituted alkene. Now what we're going to see with a big base is that our transition energies are going to be different. So let me take a look at that. So same thing, starting material is just this chlorine piece. Lower energies, the more stable alkene. Higher energies, the less stable alkene. This is all true. This is all just the thermodynamic stuff, right? So I don't change anything, even if I do use a bigger base like T-butoxide. But the idea here is that if I use T-butoxide to go deprotonate the less substituted carbons, because T-butoxide is so big, its activation, well, let me draw this first. Activation energy is this big. Let's just arbitrarily say it's that big. If you go for the less substituted carbon, that's going to give you the less stable product. The difference here is that because T-butoxide is so big, it's more difficult for it to get here, right, to the more substituted carbon, to this tertiary one. It's going to be harder, and what that means is, and by harder, I mean that its activation energy is going to be higher. It's going to have a higher activation energy because it's just going to run into more stuff. Its a transition state is going to have more things close to each other, and there's going to be more steric interactions. So what you see is that becomes a slightly slower reaction, even though it leads to a more stable product. So this becomes kinetically controlled. Right, kinetically controlled, which means it just has the lower activation energy, which is why we get this as our main product. Right, we said that what we're mostly going to see is this, which is, and all we're doing is we're just taking the fastest, the easiest route, which leads us to the less stable alkene. But it's just because that hill is lower. It's just because that hill is lower, and it's because the base is so big that looking at these transition states here, right, if I was to draw out these transition states right here, there's a lot bumping together for that transition state, but there's less bumping together for the other transition state. And so that's why we see the difference. We see sort of a selectivity based on the size of the base. But either one of these, right, they don't have any intermediates. They only have one transition state. There's only one step to this, which again is why it's a second order, because you need base to hit the substrate. That's the only step that there is, so the more of each you have, the faster the reaction goes. Now, substrate limitations, really there's not a lot, right? I don't react at the carbon with the leaving group. Well, all I really need is, I just need beta hydrogens. That's really the biggest thing, is we need beta hydrogens. So if you have beta hydrogens, you're set. That's kind of all. So for this one, here's my alpha spot. I've got a beta, and a beta, All three of those have hydrogens, so I'm good. So that'll work. I can do an elimination with that. If I look at my second one, here's the alpha spot and the beta spot. That beta carbon has 3 hydrogens on it, so that would work. Here for the methyl bromide, I have an alpha carbon, but I don't even have a beta carbon. I can't even do an elimination. So methyls, we're not going to see any reactions with methyl halides. You can't do an elimination. You can't even make an alkene, right? You only have 1 carbon. If I keep on going to this thing, I've got alpha carbon, beta carbon, beta carbon. The issue here, though, is that these beta carbons, they have no hydrogens. Right, there's no hydrogens on those beta carbons, so I cannot do that one. Yes, there's a beta carbon, but no beta hydrogens, so I can't eliminate them and make an alkene. So you just really got to make sure you got those beta hydrogens. Again, that's the big thing. Same thing here. I got a beta carbon here and here and here, so that's all good. Set. I can do that. That works. I can do an E2 on that. And then lastly, with this one, yes, I have an alpha. Yes, I have a beta that does have an H on it. But what you want to keep in mind here is that all of these ionic reactions that we're talking about, right now, they only work on sp3 carbons. And so this is not going to work, right, because that's an sp2 carbon. So if it's on, if the leaving group is already on an alkene or alkyne or something like that, not going to work. We're not going to do an elimination or substitution or anything like that on those. So for this set, right, the only ones that are all sp3 and have beta hydrogens, this you can do an elimination, that you can do an elimination, and this you can do an elimination. The other ones can't do eliminations. They might be able to do other things like substitutions, but not eliminations. So stereoselectivity. We don't have to worry about like R and S configurations necessarily because we're making alkenes, but we do need to worry about E and Z or cis and trans when you make an alkene that might have that. This is not often going to be an issue because we usually will have 2 or more beta hydrogens on the same atom. But the thing is that our beta hydrogen and our leaving group need to be anti-planar or anti-coplanar. And what that means is if you looked at a Newman projection of these things and you had a leaving group and you looked at the carbon behind it and it has a hydrogen, they need to be anti, right? They need to be anti to one another. They need to be 180 degrees away from one another. We don't want them gauche. We don't want them syn, right? We don't want 0 degrees. Well, I mean, you can do 0 degrees, but that's eclipsed, so it's a higher energy transition state, not as easy. But we need them to be anti. We need to be in the same plane, right? They're in the same plane. They're lined up in the same plane there, so that the electrons can move from one to the other. Now, in this case down here, right, with this iodine, I do have an alpha, and it looks like I got a beta and a beta. I'm gonna go look over here, and I see that I have ethoxide. So this is just OCH2CH3, right? ET is just ethyl. And so this to me looks like a strong base. So that's good. I know I can do an E2. And it's also small. There's not a lot of branching on it, right? So it's a small base, not a lot of branching. So that means I'm going to go for the more substituted side, which is this side. I'm going to take a hydrogen off of here. And the mechanism is just the same, right? Oxygen, it's going to pick off a hydrogen, the electrons drop down and kick out your leaving group, which means I'm going to form an alkene here, or I could have gotten the geometric isomer, the diastereomer, the other alkene, right? I could have gotten the E alkene or the Z alkene. And the question is which one? Which one do you think is going to predominate? When you have 2 or more hydrogens, like I do in this case, I've got 2, right? I've got these 2 hydrogens right here. It doesn't matter. If you have 2 hydrogens here, you just pick whichever one is more stable, right? So in this case, always, right? Always having groups farther away is going to be more stable sterically. So in this case, you'd expect this to be your major product. Major, minor product. You're probably going to get some Z, but not much. You'd get the E alkene, right, where they're on opposite sides of each other as your major product. But that's only, like I said, that's only when you have 2 hydrogens here, because that means that you can easily get a conformer where the H is opposite in either one of these two shapes. And so, of course, the one that's going to be easier to get to is the one that's going to be faster. So mostly, just draw the E. Just draw the most stable alkene. Now, sometimes we're going to have this issue where if I look at this, here's my alpha, here's a beta. I've got a phenyl group in there, right? I've got this phenyl group here, but there's no beta hydrogens there, so I'm not going to ignore that. The issue here is that I only have one beta hydrogen to eliminate with my leaving group. And so what I have to do is I have to make sure that they are anti-planar, that they're anti-coplanar. You might hear the term periplanar, by the way, if you're Googling around. So if you see anti-planar, anti-coplanar, anti-periplanar, that's all the same thing. Right, because in this one, the two different products I could get is that I could get a different pen. I could get an alkene that looks like this, where I have the phenols next to each other. Or I could get an alkene like this, where I have the phenyl groups opposite from one another. Right, so these are the two different isomers of the alkene that I could get. One of those two. Now, if you're looking at them, right, you should be looking at them and saying like, oh, well, this one's totally going to be less stable because the two phenyl groups are on the same side, so they're going to bump in. That's not great. And this side's going to be more stable because the big groups are on opposite sides. So probably, your temptation would be to pick the one on the right. And you may be right, but we got to check to see if you're right. You're right that it's more stable, but it may not actually be the major product of this because it's determined by having the beta hydrogen and leaving group anti to one another. So what I usually do with this is I usually take the point of view here, right? So we're going to turn this into a fissure. Again, you can do this mentally if you want, if you're really good at like visualizing this and spinning it so that the bromine and that H are opposite and then seeing what groups are next to each other. That's totally fine. That works. But if not, here's a way you can do it using the Newman projections, right? So I'm gonna do my first carbon. So I'm just converting this to a Newman. It looks to me like on my first carbon here, and let me just draw a little hair and nose, right? So you can see top of my head, bottom of my head. What I'm going to do is I'm going to look at this carbon as my front carbon, and it looks to me like I have one thing coming up and two things going down, this phenyl and this H. So for my front carbon, right, if I'm drawing this Newman projection, this is back to stuff you learned earlier, I've got a bromine coming up, down and to the right would be an H, down and to the left would be a phenyl group, right, down to the left. And that's that alpha carbon. Now if I look behind it to the beta carbon, what I'm seeing now is I see one thing going down the phenyl and two things going up, the H and the methyl. So I'm going to add those to this. Looks like my phenyl's going down, up and to the right is my H, up and to my left is the methyl. And so here's the Newman projection of that molecule. Now again, you'll notice that my bromine and the alpha hydrogen are not anti to one another, right? Right now they're gauche to one another. Right now they're gauche. They're only 60 degrees apart from one another. I need them to be 180 degrees from one another. So what I can do here is I can just turn stuff. I can just turn whatever I want so I can get it to be anti. So what I think I'm going to do is I'm going to turn the back carbon. I'm just going to rotate everything 120 degrees. So I'm just taking this back one and I'm rotating everything 120 degrees. So if I rotate that stuff around, I'm going to leave my front carbon alone. Bromine was up top, H was to the right, phenyl was to the left. Leave it. But now up and to the right should be my methyl because I rotated that back bond. Now on the bottom I have H, and to the left I have the phenyl group. And now this is perfect because my bromine is opposite of my H. Right now these are anti to one another. Right, they're 180 degrees. So everything's lined up so that this reaction can occur. But what's interesting about that is that you'll notice that this is the shape of the molecule when it reacts. Or in other words, what I'm going to see here is that the phenols are on the same side as one another. They're on the same side of the molecule as each other. And if I look at this, the methyl and the H, are on the same side as one another. So I need to find a product here, the first one or the second one. I could also write this as, right, this is the Z versus the E. Which one of these is going to be the major one? And the one that has the two phenols right next to each other is this one. Right, this is the one that has the phenols that are cis to one another, right? Same side, cis. I need to pick the alkene that has the phenols cis and that has the hydrogen and the methyl cis. So I'm going to form this as my major product. Even though it's the less stable alkene, that's the shape, that must be the one that I get because that must be the shape that it's in, which is weird. And you're not going to see a ton of these, but you might see one or two, so heads up. The book does a good example describing these, and there's more examples in the books and the worksheets too. So while you can see linear examples like that one, we also have cyclic examples. So this kind of goes back to your chair conformer stuff, where if it's cyclic, it's still the same thing. You still need the beta hydrogen and leaving group to be anti-coplanar. But what that really means on a ring is just that they need to be anti. They need to be anti to one another. Right, they can't be syn. So if one's a dash, the other has to be a wedge. That's all we're saying. Which should be relatively easy to see. Right, I got an H there. I got an H there. And so if I draw this molecule out in its chair, so I'm going to put it in a chair. And for me, I'm going to call, let's just call this carbon 1, 2, 3, 4, 5, and 6. And I'm going to call this carbon 1, 2, 3, 4, 5, and 6. So my bromine is a dash, which means it's going in the downward position, which is the axial position in this case. Carbon number 6, it looks like my ethyl is also moving in a downward position, which would be the equatorial position, so ET for ethyl. And I've got the H there. And then if I go to carbon number 2, it looks like the methyl's in the up position. It's a wedge, so that would be the axial position right here for the methyl. I'll write Me for methyl. And then its H is right there as equatorial. And so if you look at this drawing, right, at this conformer, I'm not drawing the ring flip, I'm just drawing this conformer of it. What you have here is that you have your bromine is anti to this H that was opposite of it, right? If you took the point of view right here and you look down that, that's going to be 180 degrees from one another. Again, these are going to be anti. That's anti to that. But it is not anti to this H. This H is gauche. Is gauche to the bromine. And again, I'm not going to harp on this too much right now. I mean, this gauche and anti and all that sort of stuff, just because you've learned all the chair configuration stuff before, so you should remember it. But what you'll notice is that the H is opposite. It's anti to the bromine. So that means that when you have this ethoxide, in this case, OCH2CH3, that it is going to take off this hydrogen. Those electrons are going to drop down there and kick out this bromine so that your product ends up looking where you have a double bond there, you have that ethyl group, and then you have your methyl group still hanging out over here, CH3. So that would be the major product. You're not going to get any of the alkene that goes to the other side. So you're not going to see any of this. Because that does not have the H in the right place. So again, you just need to make sure that beta hydrogen and that leaving group are anti to one another. Anti-coplanar, or with the rings, it's real easy to see dashes and wedges, right? If one's a dash, the other has to be a wedge. That's what we're looking for. So to kind of summarize this, right, E2s, they're eliminations, they're second order, they're bimolecular. They depend on both the concentration of the substrate and the base. For your nucleophile or base, you have to have a strong base. Weak bases are not good enough to do E2 reactions. So it's got to be like hydroxide or better. And it may be that if you have a hindered or unhindered one, that it makes a difference, right? So if you have differently substituted carbons on either side, remember that the hindered ones are going to go for the easiest hydrogens to get to. The unhindered ones are going to go for whichever one gives you the most stable alkene. The substrates, all you got to do is find beta hydrogens. As far as the stereochemistry, the stereoselectivity goes, if there's only one beta hydrogen, then you got to watch for that anti-coplanar stuff. But for the most part, just draw the most stable alkene that you can. And solvents, again, we'll talk more about solvents later, but I'll put it here now. The E2 reactions tend to be faster in polar aprotic solvents than they are in protic. And that's just because your base is free to do what it wants. It's not going to be solvated too tightly. And let's add it to this. We've done SN1 and SN2, so remember that methyls did SN2s real great, primaries did SN2s really well. Secondaries could do SN2s, although they were slower, and they can do SN1s. And then tertiaries, we said, could do SN1s. As far as the pronucleophiles go, we said that pretty much they only do SN1s. Weak bases, we said, could do SN2s or SN1s. And then your strong unhindered bases, we said, could also do SN2s or SN1s. And while technically your hindered ones, LDH, butoxide, things like those, maybe could do substitutions, we're realistically not going to see them do any, just because we're going to use them as bases. Now, how am I going to put the E2s in here? For my substrates, right, we just said that E2s cannot do methyl substrates because there's simply only one carbon, and to make an alkene, you need 2 carbons, so we can't do methyls. For primary, though, E2s can occur with primary alkyl halides, but because they're so unhindered, the primary substrates, E2s tend to be a little bit faster than E2s. They tend to be. So probably going to get more SN2 than E2. But with secondaries, right, your SN2s slow down, so E2s become faster than the substitution reaction. So if you have a secondary and you have a strong base, you're probably going to do an elimination. And then for tertiaries, that's even more true. The eliminations occur really, really quickly. And it doesn't matter that it's tertiary because you're not trying to get to that carbon, you're trying to get to the beta carbons. Now we just said that E2s need strong bases, so obviously the poor nucleophiles are out. The good nucleophile weak bases, out. We can only use the strong bases, which are these bottom 2. So your unhindered ones can absolutely do E2s, and E2 reactions tend to be pretty quick, so I'm putting them number 1 in order of rate for most of these, because they've got some acid-base component, and acid-base reactions are super fast. And then for the hindered ones, really, E2 is where it's at. That's usually what we use LDA and T-butoxide for, is E2 reactions, because they're too bulky to do substitutions well, but they're nice and hindered so they can just pluck off hydrogens. So that's almost always what we use LDA and T-butoxide for. And pretty much this is almost done. We need to add E1 to the substrates, but this is our chart here is almost done. And we're going to start matching these together in yet another video so we can figure out when we have this plus that, are we doing an SN2 or an E2 or an SN1 or whatever. Now some examples of E2 reactions here. I know, maybe I'll start writing this out now so you can start thinking about it. But what I'm going to do is I'm going to add here, so we've got, here this is a secondary alkyl halide, and I know that secondaries can do E2s, SN2s, and SN1s. And here I have a strong base, right? Sodium hydroxide is a strong base, and it's small. So I know that it can also do E2s, or SN2s, or SN1s. And if you look at these, both of them say that the fastest reaction they can do are E2s, which means this reaction is going to be an E2. And if I look at that, so I'm like thinking, okay, it's E2, so I'm going to remove a beta hydrogen. Well, here's a beta hydrogen, and here's a beta hydrogen. And if I look at my hydroxide is small. So you have to ask yourself, well, which one of these am I going to go for then? Does the small one go for the more substituted carbon, or does the small one go for the less substituted carbon? And the idea is that the small one goes for the less substituted carbon. You're going to take off a hydrogen here, which means your alkene, and then your leaving group's going to leave, which means your alkene should form there. So my major product should be something like this. And again, I'm going to draw the most stable alkene, not the cis one, the trans one, just because there's 2 hydrogens at that beta carbon. So that should be my major product. Technically, you do make water, and you do make sodium bromide. But again, I don't really care about the side products, it's just mostly the organic thing. So why don't you take a minute, see if you can do these last 4. Some of them are pretty straightforward, some of them are a little bit tricky, but see if you can do these last 4. Pause, do what I just did. These are all E2s, hint, hint. But let's see what the effect of the base is and where you'd form that alkene. Right, so hopefully you took a sec there to do it. This is the same substrate. I've got a beta hydrogen and a beta hydrogen, only now the difference is that I have a bulky base, right? You have a big bulky base, and so it has to go for the less substituted side, which means my alkene is going to be here, so I need to draw a different product. I need to draw that product, right, where I have the Hoffman product, the less substituted alkene. And again, it's just because I had a big base, LDA, the lithium diisopropylamide, big old base. If I look at the third one, same dealio. I've got a beta carbon here and a beta carbon here, but if you look closely, there's only hydrogens on the beta carbon on the right. There are no hydrogens on the beta carbon on the left, right? These are methyl groups. They're all carbons there. So really, this one's more straightforward. It doesn't matter if this is a big base or a small base. These are the only hydrogens that I've got to remove. So I'm just going to draw my alkene here. I feel like I'm missing one. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. No, I'm good. So that'd be my alkene. That'd be my product. Where I took it off between carbons. If I call this carbon 1, 2, 3, 4, 5, 6, 7. It should be between carbons 1, 2, 3, 4, 5, 6, 7. Right, so I took it off between 3 and 4, which is what we said we're going to do right there. Here for my fourth one, I got this ring thing. Don't freak out that it's a ring. What is kind of weird though is that it has a beta carbon up there, a beta carbon over here, and a beta carbon right here, right? So they're all attached to that carbon of the chlorine. So I have 3 sets now that I kind of got to worry about. 2 are equivalent. The 2 in the ring are equivalent because there's no difference between those 2 legs. But I've got a bulky base. I've got T-butoxide, right? This is bulky. So that means I need to go for the less substituted carbon, which is this sucker up here. So this now is going to be where my alkene is going to be formed. And I wanted to show you this one just because it tends to really freak people out to see a double bond just go off into nothing. But there's a CH2 at the end of that, right? It's a double bond to a carbon. It's just outside of the ring. That's all. But that would be your major product, where this is your double bond up here. So you have your double bond. Now, if it was a small base, then we would have taken off one of these 2 on either side of here and gotten the alkene to be in the ring as part of the ring. But in this case, bulky base, so less substituted, it's the Hoffman product. And then lastly, with this hydroxide one, and also don't freak out if you see like solvents and stuff. The solvents aren't really going to change things too much. Just focus on what your nucleophile or base is. So still have a strong base and it's small. If I want to know if I'm going to do an elimination or not, I've got an alpha carbon where the bromine is. I've got a beta carbon here where the aldehyde is and a beta carbon right there. Looks like I do have, right, and I'll draw this as a wedge here, I'll draw this in. I do have 1 beta hydrogen there. This hydrogen does not count on the aldehyde. Yes, it is a beta hydrogen, but remember we're talking about sp3 hybridized things here. So this hydrogen does not count. If you see an aldehyde, we're not going to eliminate that one. Aldehyde H's are not very acidic at all. They might look kind of acidic, but they're not. So just ignore the aldehyde H. And what that means then is since I only have 1 beta hydrogen, I have to do this whole thing where I worry about the stereochemistry, right? Am I going to form a product that looks like this, where I have an alkene that is trans, or am I going to have a product like this, where I have an alkene that is cis, right? Which product is going to be my major product? So I have to do that whole thing that I was just talking to you about, and I will add the hydrogen here so I can kind of see it. And again, I'm going to take a look here. Same thing, actually, I've got my aldehyde up with my CHO. I've got an H to the right, bromine to the left. If I look back, I've got a methyl sticking out to the right, an H sticking out to the left, and this ethyl sticking down on the bottom. Again, I'm going to rotate so I get the beta hydrogen and the bromine opposite. So right here's the bromine, here's the beta hydrogen. Right now they're gauche. So I'm going to rotate, in this case I'm going to rotate my front one. I'm going to rotate my bromine to here, H to here, aldehyde to here. I'm going to leave the back one alone, so I'll just draw the back one first. right? I still had the H, still had the methyl, still had the ethyl. Oh, sorry, I should have had, I forgot something on these products. Methyl, methyl. Don't want to lose my carbons. And then on my front carbon, it looks like now where the bromine was, now that's where the aldehyde is, the CHO. And then over here is the bromine, and up here is the hydrogen, which now, thankfully, puts my bromine and my hydrogen opposite of one another. And then this is where I find the things that should be cis to one another. Oops, sorry about that. The things that should be cis to one another, right? In this case, the H and the methyl should be cis. And in this case, we should have the aldehyde and the ethyl next to one another, which means this is going to be my major product. That's going to be my major alkene, where I have the ethyl and the aldehyde on the same side as the alkene, and the H and the methyl on the same side of the alkene. So that's E2 in a nutshell. Absolutely practice, practice, practice. I'm so sorry this was such a long video, but there's a lot to say about E2. Practice, take notes, write down your questions, and let me know what your questions are, right? Talk to your study group folks, email me, or come to office hours or study sessions. All right, happy studying and good luck.